Okay, in this concept we're going to talk about perpendicular and angle bisectors. A perpendicular bisector is any segment that is perpendicular to any other segment and bisects it at the same time. So let's look at what we have here. So we have a segment AB, right, the horizontal segment, right? And then we have segment DE, perpendicular to AB at point C, okay? And also bisecting it. So segment DE turns segment DB into two segments. So AC, right, and CB, or BC. Okay? Two segments, equal segments, because we have the same dash. So segment DE bisects AB at point C and is perpendicular to AB. If a point on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So again, we have the perpendicular bisector, this guy, and then we have the bisected segment, right, this guy, so AB. So again, if a point is on the perpendicular bisector of a segment, so any point on the perpendicular bisector, but it has to be on the bisector, okay? Please excuse my rough sketching, right? It has to be exactly on the bisector, any point, this point, this point, this point, this point, this point, etc., etc. Okay? So any one of these points is equidistant from the endpoints of the segment. So these are the endpoints of the segment that is being bisected. Okay? So this point is equidistant from here and here. So look at that, isosceles triangle, right? So is this point. Isosceles triangle with this segment and this segment. Okay, let's make two dashes. Same for this point. Again, excuse my sketching, but hopefully you get the idea. Right? This point, this segment, and this segment, isosceles triangle. This guy, right, AD and BD, right, isosceles triangle. So any point you pick on the bisector, and then if you connect that point to the endpoints of the segment, of the horizontal segment, you get an isosceles triangle, right? Which is very nice because isosceles triangles are great. I mean, they, everything is symmetric when you draw a perpendicular bisector and get an isosceles triangle out of it. Or if you draw it in an existing isosceles triangle, everything is symmetric, right? All the angles are symmetric about the bisector. Basically, you have two congruent triangles, right? So if this is an initial isosceles triangle, right? If this is equal to this, and this angle is equal to this angle, then if you drop a perpendicular bisector like this, right? Then everything is symmetric, right? So obviously both of these angles are right angles. This angle is equal to this angle. The area of this triangle is equal to the area of this triangle. Everything is symmetric. So it's very nice. Simplifies things immensely. Let's look at this example. So DE is a perpendicular bisector of segment AB. Find the value of x. So again, with it being a perpendicular bisector and then point D, right, or this point actually, doesn't have to be point D. Well, actually it is point D, but I guess the drawing should have just, put it here, which is fine. So point D is equidistant from A and B since it is on the bisector. So that gives us AD is equal to BD, right? These two segments are equal. So then we can write an equation, right, based on the given lengths of the two segments. So 3x plus 5 equals 2x plus 14. And then we just solve for x, and then in the end we get x equals 9. Okay. Here's another feature of bisectors. So in this case, we'll be talking about angle bisectors. So an angle bisector, again, is a segment that breaks an angle into two equal angles. Single angle into two equal angles. So a point that lies on the angle bisector of an angle is equidistant from the sides of the angle. Right? So if I pick any point on this angle bisector, and I find the distance between this point and any of the sides of the angle, right? And to do that, I have to drop a perpendicular line that is perpendicular to the side of the angle, right? So it has to be perpendicular like that, not perpendicular like that, okay? It has to be perpendicular on the side of the angle. So like this, for example, right? This is perpendicular. So any such point is going to be equidistant from the sides of the angle. So this is equal to this, right? Just like this is equal to this, okay? So again, if AD is an angle bisector of angle BAC, then BD equals CD. BD, which is this guy, is equal to CD, which is this guy. Okay, let's look at this example. AD is an angle bisector of angle BAC. What is the value of x? So again, bisected angle, angle A, and this happens to be a point on the bisector. Therefore, BD has to equal CD. So we can just write an equation, 2x minus 3 equals x. Solve for x minus x minus x plus 3, right? 2x minus x is x. These two cancel, and we have plus 3. X equals 3. Right? So 2 times 3 is 6, minus 3 is 3, and then x equals 3 is x equals 3. Okay? And just like what we have here. Alright, and here we have some exercises. Please pause the video, work on these, and come back for the solutions. Alright, so here we need to find the length of segment BD. So again, DE, segment DE, is a perpendicular bisector of segment AB, right? So CB equals CA, and this is essentially an isosceles triangle, right? Because a point on the segment, point D, is equidistant from the ends of the segment. So we can just write x plus 2 equals 4x, okay? Minus x minus x. 4x minus x is 3x equals 2. X equals 2/3. Okay. So if x is 2/3, then BD is equal to 4x, which is equal to 4 times 2/3, which is equal to 8/3. Okay. Next exercise, we have this triangle, or this shape, two triangles obviously, but essentially it's a bisector of angle A. Okay, so AD is a bisector of angle A. And we need to find segment BD here also. Okay, find segment BD. So again, since this is an angle bisector, we know that BD is equal to CD, so we can just write x plus 14 equals 3x, right? Minus x minus x. So 2x equals 14, so x equals 14 over 2, which is 7. Okay. And this is it for this concept. See you in the next video.